All right, cool. So, welcome to all of you. All, plural still counts. Sorry about like last minute rescheduling this today, but yeah. So, welcome to. It's the first time we're gonna try and give this talk. It's like an introduction to game development. It's a very broad kind of look at very like high level beginner overview of kind of like game development, games, what makes games, and then I'll look at some common techniques that we can apply when programming games. More specifically, taking a look at the introduction assignment, the assignment that most of you guys had to do, the roll a ball with added functions. I'm gonna try like or looking over it. There's a lot of not mistakes, but common like common quote unquote mistakes that some people might have made, not knowing how some things work. So I'm gonna try and go and like show maybe some different ways, some quote unquote correct ways to do some things. But before we get to there, let's start with the basics. So, um, games. We're all working on games. It's most of us know when we have a video game in front of us, we know what a video game is. We know what a game is. But um, when asked to define it, it's kind of sometimes more nebulous to define what a game is. You can say this is a game, this is not a game. Your calculus assignment or whatever assignment is not a game, but Tetris is a game, right? So, what defines a game? There are some people who try to give some definitions to games. Some people try and define it by the fact that you have rules, which regulate what you can do, and you have goals with what you want to do, with what you want to obtain. You have a goal that you're trying to obtain, trying to do, and you have rules specifying what you can and cannot do in this world, in this game, whatever you're doing. And this applies to both video games and games in real life. So, like dodgeball or tag, chess, or, Halo. Another aspect of games which is very hard to define is fun. So, most of us play games because we find them fun. That is sort of a distinguishing factor between um, games generally and other mediums such as books or anything else. Video games maybe there's other reasons why you might play them, but like oftentimes you play I don't know, hide and seek because it's fun, right? Um, but fun is a very, like I said, very nebulous, very difficult term to define. People often try and define what fun is, but they can't. There's no real theory. So fun in the end often ends up being the release of endorphins into your brain, right? But why? What sort of generates that kind of fun is often left up to debate, and many people theorize about different reasons for it. At the end of the day, um, part of making a game, part of the art of making a game, is trying to find what the fun is. Trying to make a fun game versus making just something that's boring, right? Like an assignment. Very famous quote by a guy called Sid Meier, who made the Civilization games, is that games, fun in games, it's a series of interesting choices. That's basically what it boils down to, according to him. You have a bunch of interesting choices you're always doing when you interact with the game. Every time you interact with the game, you have a new interesting choice to make. And this applies against video games or um, offline games, whatever. Offline games, traditional games, chess. You always have an interesting choice to make, right? Like hide and seek is like, what am I gonna look for next, right? But then there's another level of interesting choice, which is where would this person that I know, where could they be hiding, right? So that's according to our good friend Meyer, and he's made some fun games. So you might know a thing or two about it. Now, so I've been talking about traditional games, but we want to really look at now, like we're talking about video games. Like I assume most people here are not really like making chess 2.0. So so what distinguishes a video game, and that's basically, it's the fact that it's on a computer. It's the digital revolution, if you want. That's what really created this new thing called video games, which is a game that runs on a computer. So games as a forgot to fill out here pictures of games from different eras. old PowerPoint was gone, so I had to kind of remake it from what I had left. But anyway, that's the next slide. I have pictures. So games are basically as old as human society. We've been playing games as humans for as long as we can remember, regardless of how long you think humanity has been. As long as that's been, we've been playing games. It doesn't matter. We've always found games that people have been playing. And so for that reason, some people think that games back then had, and even now have, an evolutionary advantage, which is maybe why we find them quote unquote fun, is because games prepare us, they help prepare us for situations which we might live in real life. Now, you probably won't be jumping on on people's heads anytime soon, but the point is that it's an abstract problem that you're trying to solve. They're just trying to solve, by thinking about it, and then eventually you might encounter some similar kind of problem in the real world. Probably not like, Tetris, you can find some instances. Halo, hopefully you will not find a lot of instances where you have to apply those. Maybe paintball. Assassin's Creed, definitely. Depends on how much you hate your siblings. But so in 1972 is the creation of the first, quote-unquote, first video game, often attributed to Pong by Alan Alcorn. So Pong was a ping pong game where you had two little bars and a ball going between them. That was the first video game because it was the first game, so it had some fun, running on a digital machine. So,
It was a huge machine.
it was pretty big. Yeah, let's say bigger than my MacBook, or maybe this room. Actually, the original Pong was running on. Was it running on something equivalent to like an oscilloscope or something? I don't remember. It was running on something very old. It was not like a traditional computer. But point being, since then, games have changed quite a lot. Computers, as you may know, have gotten much more advanced. The phones in our pockets are better than a supercomputer from like 30 years ago. And despite the great crash of 1983, which if you ever read anything about video games, you'll hear about the crash of video games in 1983. Video game industry has kept growing every year. It's now a bigger industry than movies. People all around the world play games. Games are huge, multi-million-dollar projects often. And today we've started having the first generation of people who've grown up with games. Who are adults, so people who were kids and now are adults, and then those adults who had kids and are growing up with games. So you see games influence a lot more in pop culture and everyday, what's his name? The famous comedian who passed away, unfortunately, named his daughter Zelda. Cannot remember his name. Famous U.S. comedian. Gonna hate myself for forgetting this, but anyway, he named his daughter Zelda after the video game, not after some random Zelda. We have an Assassin's Creed movie, we have Pixels and an Emoji movie or whatever, but and everyone plays games, and nowadays, regardless of what you consider a hardcore gamer or not, everyone plays games on their phones, or everyone plays video games. Everyone is a quote-unquote gamer. Everyone's a consumer of video games, pretty much, at least in countries where you can afford to have a computer for most people. So yeah, these are some examples of games and where we've gone. So Pong, 1972, top of the line graphics back then, something you could probably do in in Canvas today. Prince of Persia.
How do you know? Did you do that?
Pong? No, I didn't make Pong, but I think if he was able to make it in 1972, you should be able to make it in a Canvas and HTML today. Prince of Persia, 1989, made by Jordan Mechner before it was bought by Ubisoft. It does look a lot more complicated, and actually the technology between 1972 and 1989, even though 1989, computers were not that crazy advanced, they were still leagues ahead of what 1972 had. And in 1989, he was able to use a lot of new technology, he was coding in assembly, which meant he wasn't coding, he wasn't, using punch cards or anything. He actually recorded animations using video and rotoscoped them into the game, you have a colored game running on a computer. And then we flash forward, what is that, like 30, 37 years to 2016. You got Uncharted 4, which, looks pretty freaking good. And you have games like Stardew Valley, which might not look super realistic, but just goes to show that we have today compared to before, we have a lot more advances and we have a huge freaking variety of games to choose from. We have more games today than any other time in human history. Too many games. Go on Steam, you'll find so many games. So who makes all of these games? Game developers. So who makes a game? If I ask you who makes a game, you're gonna say it's a game developer, right? Obviously, like who builds a building? It's a builder. Duh, right? But actually, like game developer is a term that just englobes anyone who has worked on a game. But it, hello, you guys here for the workshop?
Yeah.
Cool. Take a seat. No, unfortunately not. Sorry, guys. So, so who makes games? Game developers. You guys do not. Those two seats, by the way, are not. You don't have to sit there. Like, don't feel bad about it. You can sit anywhere. So game developer includes a lot of people. So for most people, it's usually it counts programmers, right? So most people here are programmers. So, and even in terms of programmers, there's tons of kinds of programmers. You've got gameplay programmers, engine programmers, physics programmers, graphics programmers, network programmers, tools programmers. That's if you look in a huge company like EA, 343, Ubisoft, Square Enix, whatever. You got those kind of programmers. But then if you go look at an indie company, you've got one dude, three dudes. They don't have a title. They're just programmers. They're just doing everything, right? We've got designers. So I was talking about what makes a game fun. Well, there's people whose full-time job it is to kind of, like someone would plan out what's going to go in a book, right? Like a storyteller writes a story and plans it out. A designer writes out what are these interesting decisions that we're going to make in games. What are these interactions that we're going to have? And even then, you've got like tons of kinds of designers. You've got level designers, mission designers, designers for like economies, really anything. A designer for any big section of your game that you define. It could be different. You could have designers for a game which they're not designers for any other game, right? Then we have like people without whom your games might look like Pong for the rest of your life. You've got artists, tons of different kinds of artists actually. You've got and when I say artists, I'm specifically referring to kind of like drawing or 3D art. Music is another thing completely. Not saying it's not art. It's just traditionally, when we say artists, we mean like that. We've got 3D artists, 2D artists. So kind of what dimension you work in. Hello. No, definitely not. Sorry. It's the game developers without borders meeting. So you got artists divided by like how many dimensions they work in, and then based on their specialty, you've got like in 2D and 3D you go get like level artists, character artists. Some people are better at drawing like environments, some people are better at drawing characters, depending on what style, 8-bit, realistic. In 3D you've got animators, prop designers, technical artists. You've got tons of people for all the million things you have to do. And this is in a big company. And then you might find in a tiny company you've got two artists who are doing everything. We've also got writers, musicians. Really, there's a shit ton of people who work on games. And it really depends on each game what people do. For example, if you look up Assassin's Creed Origins is coming out soon. It's a new Assassin's Creed game by just another one of those Assassin's Creed games. And they've been making a lot of advertisement about how they spent a lot of time looking into ancient Egyptian mythology and history and hieroglyphs and all of that stuff. Yeah, I'm guessing you're Egyptian, yeah. And so what that means is that there's people at Ubisoft whose full-time job on the game is supposed to be a historian, right? Otherwise, there's a guy at Ubisoft whose job it is to whack things together in a sound booth to generate sounds, right? So there's actually tons of people, like depending on what is required for the game. For example, Eve Online. Have you guys heard of Eve Online? It's a huge, it's a massively multiplayer RPG kind of life thing, if you want. It's not like The Sims, but it's like you own a ship and you live in this like space economy kind of thing, and very realistic. People often call it like a spreadsheet kind of game. Their economy designer, I think, ended up becoming like the finance minister of that country or something. Uh, or he ended up working at Team as a finance manager. So anyway, like they had a dude whose sole responsibility was to manage the economy, just like they have an economy minister here in Canada. Like they had one for you. Point being, tons of people who work on it. Now I'm gonna sort of flash forward. This is kind of a very rough overview of game theory, sort of understanding kind of games. Like, I mean, if you've played games and if you're interested enough in them, you've probably touched upon these subjects at some point. There's a huge field of game theory which has nothing to do with programming or like art, which just has to do with like some of it has to do with the history of games. So games have started being old enough that we can look at the history of games and how games have been inspired. Like games today, like back maybe it was hard to call Pong back then art, but games today have gotten to a certain point, like visually and in terms of like depth, that it's very fair to call them art. And once you call something art, then you can start studying like the influences and why do people appreciate it, and then there's certainly maybe more of a reason to play a game than just for fun. So a lot of these things are called, so it's a study of games. It's like game theory. You've got people who study game design, again, what makes games fun. We can't really, I mean, today's not entirely about that. I just want to kind of have a brief overview of it. But there's tons of information about it online. I might at some point have game designers come and give a talk. Some people like whose job it is to be a game designer come give a talk about like what is their job, because you know, like a game programmer, it's hard to sometimes say like, oh, I make a game, then like what, like I program, right? I write code. Like, oh, okay, sure, right. Then you're like, I'm a game designer. It's like, what do you do? It's like, well, like I say what they, it's like, oh, you just tell them, you tell the programmers what to do. That's your job. Like you just like write, you say like make the game fun. Is that it? Like, you know, it's harder to describe what game designers do, but it is a critical job. So yeah, so I might have someone come talk about it at some point. Now fast forward, jump basically to something else a bit more technical. So I'm gonna talk about the core, the engine that powers a lot of games. So how many of you guys have heard the term game engine? How many of you guys have heard someone talk badly about a game because of the game engine it was made with? Yeah, have you?
I think I heard something like that. Yeah.
You? What game engine nowadays are people fans of hating on?
The ones I was thinking of for me was Unreal.
Oh, you hate on Unreal?
Not me personally, but I've heard.
You heard of people hating on Unreal? Okay. So game engines are a very special thing because it's become a thing that people sort of know because game developers talk about the engines that they use. But a lot of people don't kind of, not like they don't know, but they sort of start to assume that, oh, a game engine is your entire game. Oh, you're using Unity. Every Unity game is the same. It's all using Unity, right? Like that. It's a game engine. Like it's powering it. Yes and no. So a game engine is, I pulled this definition off of like Wikipedia. It's a software framework designed for the creation and development of video games. So I'm gonna give you common elements that are in a game engine. But if you notice from the definition, it doesn't talk about any of these elements. Because a game engine, basically what it is, it's a set of code. It's a bunch of tools, a bunch of code that you can use to build your game. It doesn't have to be useful necessarily to make any other game. It just has to be useful for the game you're working on right now, right? That's at least my definition. That's the way I like to see it, which is why when people talk about like Unity, and like, oh, you're using Unity. It's like, yeah, but I've written a bunch of code that I put on top of Unity like the code that I write that I start reusing between my games that I like that may be less specific, that becomes part of my engine. Every time I write, for example, let's see, if I write some AI code that is not present in Unity and I use it in different games, well, that's part of my engine. If you're working in JavaScript, for example, in Canvas, and you're writing a bunch of stuff to be able to make your game, right? That is sort of your engine. It's not the traditional kind of engine we see. It doesn't have an editor or stuff like that. But at the end of the day, that is kind of what's powering your game. But in terms of more traditionally what people think of engines, actually, I mean, people who are not very technically, like they're not really programmers, they might not know this at all. But a game engine, basically, it provides you with core functionality to make the game. Engines like Unreal 4, Unity, ItTech, Crytek, RPG Maker, they all have some things in common. The biggest thing in common that they have is something called a game loop. So if you've ever written a game from scratch, I mean, I know you personally are writing a game from scratch, right? At some point you have somewhere in your code. At some point in your code, you have something that says while true or while game is running, right? That is the basic. Any game at some point in that code somewhere has a while game is running, and that is the while loop. And inside of that while loop, we have a bunch of updates, and we have a bunch of stuff that runs, and that's the functionality that the engine gives us. On top of like the stuff that's while it's running, the engine can help us load assets, visualize things before we work on it. So a lot of things like physics, animation, AI, serialization. You might not be familiar with all the terms, but like these are all tools that the game engine provides. And like you kind of get it, it's tools. Like it's basically providing you tools to kind of simplify the making of your game. Whether if you guys have any question at some point or like are falling asleep, let me know. Don't worry about it. So let's look at the game loop. A game loop, like I said, is that's the main thing your game is running on. Every game at some point has a while game is running or while true. And inside of that loop, you have you're updating things. So you've probably all heard of the term like frame rate, frames, right? Rendering. So that kind of comes from the game loop. So every game loop at some point has to draw stuff on the screen, right? Has to tell your computer, hey, update what's on the screen. Depending on how fast that loop runs, right? Every time it goes back to the top, it tells the computer to draw again. Depending how fast it can get back to the top, determines how fast your screen is going to update. Thus, where we get the term frame rate. How many frames can you generate for a given moment? Then you get frames per second, which is how many frames can you get in a second. How many times can you go through that loop in a second? This is a kind of like more modern games. It's not exactly like that, but it's a very it's a good way to think about it because that's kind of how it works. So other than rendering the game, other stuff you have to do in it is like update physics, update AI, update game logic, update anything that needs to be updated, which is where sometimes you might not be wanting to use a big game engine like Unity. Unity is updating a ton of stuff in its game loop. Unity is updating everything it's implemented in its game loop. It's updating, it's always updating its physics engine, even if you're not using its physics engine. It's always going to update its physics engine no matter what. It's always going to update, it's always going to run updates for a lot of things, even if you don't want it to do it. So maybe at some point you want to write your own code without Unity because you're like, hey, I don't want to write, I'm not using your physics engine, I'm using like my own stuff that will run faster because there's less stuff to run. Even though Unity is optimized, like most game engines are optimized, they're generally made for a specific kind of game, and they're assuming you're using a lot of their features in a specific kind of way to make use of that optimization. So often if you just don't use a lot of features and re-implement them, it sometimes tends to be like slower than if you implemented it on your own. And by slower, I mean like for the computer to run. It's not slower in terms of how long it would take you to write it, because writing something like Unity would, as a single person, probably take you a couple of years. So this is kind of the, oh my god, this is the game loop inside of Unity. If you must have all at least used Unity once, most likely. You've probably touched at some point in a void update. That's part of the loop. That's when Unity goes through every single game object and tells it, hey, update. That's part of the update game logic loop. It also, you might have seen at some point an update physics, update late physics. That's when Unity goes in and updates its physics engine, and afterwards it tells all of its game objects, hey, I've just updated physics. You want to do something after the physics? Oh, no problem. This is the general, this is not the entire loop, but this is a general way to kind of see how it works. So if you look, you've got the physics here, you've got input events. Basically the idea is that Unity goes in, updates its physics, gets all of the inputs from the player, updates the game logic, so your update, late update, whatever, renders the scene, so draws everything on the screen, and then does some editor stuff, which is the gizmo, updates the UI, finishes the frame. If you're pausing, this is where it pauses, and then it goes all the way back up to the top. And that's the game loop in Unity. It's a complicated game loop because it's a pretty full game engine. So more about Unity, because a lot of people end up, we end up using Unity for a lot of things because it's an easy to learn game engine, and it's in C#, which is a very nice language. That's kind of similar to Java in writing, but it's nicer. So what's nice about Unity is that it lets you prototype games quickly. It's multi-platform. You can deploy to anything. Oftentimes, what people blame it for is that it's less optimized and less powerful than certain engines like Unreal Engine. I'd say for a beginner, you often won't see the differences. Unreal Engine is a lot closer to what you will find in like in a big studio. Like it's a AAA kind of engine. Not to say you can't make some games like that in Unity. Some games you can't make in Unity just because of the way it's built. It's hard to support some types of games, like huge multiplayer games. Often is very hard to do in Unity just because of the way it's built. And Unreal is in C++, which allows you to do some other things that you can't do in Unity. But in general, it's a very good game engine. You can do a lot of stuff, and like for beginners, oftentimes like are like, but Unreal is better. I'm like, listen, you're such a beginner that like, no, there's no difference for you. Like honestly, there's no difference unless you've gotten to the point where you're talking about like the rendering and like how Unreal does its like post-processing effects better, or like how it renders its stuff better, or you're like working with like some very specific stuff that's like more advanced you might not know. Going back to a bit more theory, you guys have all worked with it. Unity and a lot of game engines work with what's called a component-based thing. So a way to visualize it, a way to think about it is that Unity provides you with a scene. Okay, you've all worked with Unity, you've all seen the scene, which is like a movie set. You've got a camera that's filming everything that's happening in the scene. Everything the camera can see is going to be in the movie. And so there's stuff in the scene that the camera can't see. All these objects that you put in the scene are called game objects. And they all have components on them, which are like add-ons if you want. It's like, say like, my phone is a game object and I can like attach I don't know, a spinning blade onto it. That's like an added component. All these components belong to the game object and are used to modify its behavior. And they'll all have, like I was saying, you've got like the update loop, and they'll all go through a sort of step. Every update of the game, they're all gonna go through like certain functions. So they're all gonna call updates every frame. Late update after the physics every frame, on awake when you enable a game object. And you can use these to kind of like build the logic of your game like you most likely did. Your scripts are components, and that's how you add them, and that's how you interact with the game. Is this the best way to do games? Are components the best way to component-based programming, the best way to make games? Not necessarily. There's some people who do it without it. But it's a pretty good way. It's a good way to visualize how it works, and it ends up working well. The times where it doesn't work well, you'll know very quickly because you'll be trying to do something and you're like, oh, this is weird. But yeah. So I'm going to skip kind of this part. Get components. You can get a game object, and then you ask for the game component on it. I'm assuming I think this is okay for most of you guys to like get the component on a game object. Anyway, this is something you can like fairly easily Google, because I want to skip to the next part, which is the idea that now I want to touch upon like kind of how to do some stuff in games. There's a lot of way to do stuff in games. You want to achieve a goal. You want to make your game do something. There's tons of ways to do it in a game engine or whatever. You've got like tens of ways to do it. No one way is the best. There's some ways that are better than others, that run faster, that are maybe easier to write. I'm gonna look at some, like kind of how. So for the assignment, we asked you guys to do a few things. I'm gonna kind of look at like what's one decent way we could have done these things, and add a bit more to it, and like kind of why did we ask you guys to do this, kind of hinting towards something else. So first thing that you guys had to do after finishing first thing you guys had to do was to finish the rollerball tutorial. It's pretty simple, I think. Second thing to do was to make all the cubes rotate randomly. So why do we want to make all the cubes rotate randomly? Because it's boring to see all the cubes rotate in the same direction. But also, a lot of people, what they did was they kind of went through and they rotated the objects so that they had an initial orientation that was different. And then, so if you have one object that's like, my fist is like this and it's rotating like this, and my fist is like this and rotating like this, they kind of look like they're rotating differently. So it kind of achieves the point of like they look different. But that requires you to go through 25 objects and manually rotate them. Which, I mean, some people's job is to do that. Often designers go in and tweak things, but for things like that, we kind of want to simplify it and like not do it by hand. Right? You're a programmer. If you're a programmer, you want to speed up this process and kind of find a more procedural way to do it. And this is a very important thing in games because you've got a lot of games that do utilize this concept on a much more complicated level, but like it's the same idea. It's basically like I want to have a terrain. I want to generate a terrain. I want to have a different terrain for every player because it's cool. I want every player to feel like he's on his own planet, right? But I don't want to ask my artist to draw like 20 billion planets. That's not realistic. It's going to take way too much time. So we're going to randomly generate them using some procedure. I don't know, Michael, how many people showed up? So we can use a few things. So for the rotation in the game, the most basic thing we could have used is actually random.range, which is going to return you a random number in a range that you specified it. I'm going to show it. So let's open Unity. Have it open here. And show. Let's open Unity. Okay, so I was kind of working on this right before, but so we've got the cube 1 here. Okay. And I just downloaded the rollerball tutorial online. This is the one that comes with, this is the Unity one, like the basic one, and it's rotating, right? I want to rotate it in a different direction, so one thing I could do is I could, it's not going to be visible, I'm rotating the wrong cube. I could, it's not going to be visible, x-axis, 45, and then z-axis, 45. I do this, I run it again. It's going to sort of look like it's rotating differently, but really it's rotating around the same axis. We don't want that. One thing I could do is, so here we've got transform.rotate, and it's rotating it by a certain amount. So one thing I could do is I could say, okay, let's use a public vector3 rotation and say rotated by that amount. It's going to compile, and now it's going to let me tell it by how much I want it to rotate, which is sometimes this is a way used in games because you define a property. You say, like, for example, I have a gun and it has a fire, like you don't want to fire as long as you can. You want to fire every 5 seconds or like every specific set of time. You define a fire rate and you let the designer decide how much you want. So we can do it like this. That's neat, but it still comes back to us having to do it manually on every object. So I'm going to look at this. Let's look at this cube here, which is disabled and invisible. to which I'm going to add a random rotator thing. So what are we going to do instead is what we're going to do is we're going to, this rotation amount that we want to rotate by, instead of having someone set it, we're just going to randomly generate it when we start the game. So we're going to randomly generate a vector. I'm assuming most, like, you guys should all be at least familiar to some level with linear algebra, right? Anyone here not know what a vector is? It kind of be difficult. Yeah, no, you don't know what a vector is.
I do.
I was just pointing. Listen, I'm open to it. So you're gonna randomly generate a vector. I'm gonna normalize it, so it gives me, it's a vector of length 1. Because I don't want it to like give me a vector that's like super long. I just want, in general, what I want is the direction of rotation. And then I'm gonna multiply it by speed, how fast I actually want to rotate. And this is a public thing. This is something we can say like, hey, I want all these cubes to rotate at 5, but if you want to go and make them like rotate at different speed, it's still kind of a good thing to like not have everything randomly generated, you know, like you can have some people tweak it. And you can really use with a mix. I could have defined here like min, max, and put those as fields, and then someone could have specified them, and that it would have worked. But so if I run it here, it's compiling. It's running. What did I do wrong? Rotation amounts. Did I avoid updates? Kind of copied this right before. Rotator. Let's see. If this doesn't work, we're gonna have a nice session of debugging why it doesn't work, because it was working like 5 seconds right before. Let's see. Am I running? Okay. Oh, it's rotating just really slowly. That's what explains why. I'm just gonna move this speed here. So I put the speed in the start because I didn't want to. I mean, it's more optimal, but I'm gonna change it here so we can actually see how it changes real time. So it was moving. It was very slow. So if I change this to 50, there we go. It's rotating, and if I disable it and add another random rotator script, we'll see that it's rotating in a different direction because it's going to be different every time you run it. And if I just duplicate this object, in theory, unless I've messed up my stuff, it should all rotate differently. So if you look here, actually it's easier if I put them all at the same position. You'll see that they're all they're not aligned. And since they're not aligned, that means they're rotating in different things. Yeah, it looks funky, but you kind of get the point. So that's one thing, that's for the assignment, right? So that's how you could have done it. That's kind of the way we were trying to hope to get it, and you'll see that like it kind of simplifies things a lot more. You don't have to go change them manually. This is maybe less interesting. So instead, what I'm going to show you guys now is how do we apply this to do some how do we apply this kind of principle of randomness to do some slightly more interesting stuff, like generate a terrain. So conceptually, a bit more advanced, but the idea is still there. I don't want anyone to draw this by hand. I want this to be randomly generated by the computer, procedurally. So procedurally generated, like Minecraft, just means the computer is running through some algorithm to generate it. We can do this actually fairly simply with some other, this is the wrong PowerPoint, with some other kind of random function. So I'm not going to explain the entire details of it, but there is,
Which one is it?
huh?
What's the generation algorithm?
It's a Purlin. So we're going to use something called a Purlin noise algorithm, which was created by some dude for movies, actually, and he won an Academy Award for it. So Mr. Purlin saw that all the artists working on movies, when they wanted to make clouds and stuff, they were working endlessly, like what I was saying, right? They want to make something that looks kind of random, right? they had to do it by hand, and it took them ages. Like to do wood, you know, like you want to do wood, you don't want to use the same texture because you don't want all your wood to look the same, right? You know, you want the floor to kind of look the same because it looks clean, but in a game, like to make some, like you want to make a tree, you don't want to have every tree have the same tree trunk exactly. That's boring, right? So back then, people like artists would draw this by hand in movies. Mr. Purlin was like, "Nuh-uh, I'm gonna put you all out of a job," and he decided, I want to do this randomly. So he decided, let's use noise. So noise is just randomness, right? You turn on your TV, it's not working, you see like white and black, right? That's noise. That's like electrical, that's your cable detecting electrical signals. They're kind of random and like outputting them, and it looks random. But if I took, so if you remember your TV, right? It's black and white. If I took that and tried to make it doesn't look like a cloud. Like I can't make anything out of it. It's too random, right? We want some randomness, but we want like fake randomness. We want like a sort of, it's not pseudo randomness because that means something else. We want randomness that has a sort of trend. We don't want the randomness to change too much. We want like, okay, like here is black and over there is white, but between them is like sort of gray. You know, we want this, not like a pillar here and then like here it's like the depths. You know, like in Minecraft you see it as like, if you look from far, it looks like you have like, just like here, you have a general tendency. You have a general tendency of like something, right? And even within the little details, like see here, you have like a little bump, right? So we kind of want to do that. What Mr. Purlin did was he invented an algorithm called Purlin noise, which basically results in something that looks like this picture here. So this is noise, right? But it looks more like clouds, right? And the details of the algorithm are like a lot more complicated. I'm not going to go through them, but in general, we can use this, right, to do things like generate terrain, or you can use it for anything else. You can use it to kind of maybe define a random movement. But the point of this is that if you see here, you've got like this black zone and you've got this white zone, and it's not like just black dots and white dots. There is like a sort of trend. It looks like clouds, right? It's like there's like detail and there's like a general trend of randomness, but there's still like there's a trend, right? That's the point. It's random but with a trend, and there's still information. So how are we going to use this? I'm going to show you that thing that I did uses like, how many lines of code is this? Like not many lines of code. There's 4 lines of code. Like you can do the thing that I generated and 4 lines of code. To show you like that, you guys can't see it right now because PowerPoint is, hello? I'm going to end show. So yeah, open this. So we have this function here called, it's like random.range. Random.range, they have a built-in Purlin function, which is neat. So instead of using random, which will give us a random number between 0 and 1, and if you give it a range, it'll give you a random number between that range, we're going to use Purlin. And Purlin, what it does is it takes an x and y value between 0 and 1, and it's going to give you a value between 0 and 1. Pretty simple. So if we look back at the picture, if I make it bigger, 0 for the x to 1, and 0 for the y to 1. And then here, this value of black and white, 0 for white, 1 for black, or 0 for black, 1 for white, right? And then like the gray is everything in between, right? Everyone pretty good with that? Not too complicated? So if I mapped this picture and said that each point, instead of a color, it was a height, you kind of start getting the idea of where I'm going. If I just give a height instead of color, I will get this thing here. And I mean, I'll show you just, you can kind of also play with some factors of it. So if you look at the picture here, there's like global trends. So you have this big black area and this white area, but even if we zoom in, you see how like within the black area you have smaller trends. So the nice thing about Purlin is that there's macroscopic tendencies, there's also microscopic changes. It's really cool because it allows you to get this like sort of an environment where you have like hills, but within the hills you have bumps. You know, it's not just like a smooth thing. So that picture that I was showing you earlier, that thing here I was showing you, is like mostly smooth, right? But if I wanted to add some stuff in it, I could. If I wanted to make it more interesting, have it more bumps, I can change the value, and now it looks like this. Because this is basically equivalent to me zooming in on the picture, like I did here, like I did with this. If I look at it from far, that was regular, but then if I zoom in, that was when I changed it. So you see a lot more bumps. So going back to the code, what I did was I basically I defined the width of my area. So I say 500. We can forget about this mod scale for now, modification scale for now. I defined a prefab that I'm going to spawn in the world, and I'm just using a cube. Okay. I just so I know for the code, I said how big is this cube, but it's basically going to let me know how much I need to distance each object from each other. And then I said, okay, I'm going to loop over an x and y area from 0 to the width, so I'm going to get like 500 times 500 square, and I'm going to create a new object that I'm going to position at like xy, you know, like ij, whatever. And then I'm going to modify its y scale by a value that Purlin noise gives me. And then the inputs of Purlin noise are going to be that I and j divided by the width, so we can get it between 0 and 1. But like basically the point is it's like I and j, right? Like I'm giving it I and j, and it's going to give me a random value. Actually, for this Purlin noise function, you might be able to give it like any values, but pretty sure, usually it's between 0 and 1. So that's what I do. I just do scale.y is equal to mathf Purlin, and I get the I and divided by width. I get the j and divided by width. I ignore the mod scale for now, and I multiply it by 100 because it's going to return a number between 0 and 1, and I want it to be visible. So like 0.43 is going to become 43. And that gives you basically what I got. Here mod scale is basically so that we can achieve that like zoom in that I told you about. So if I give 0.1, 0.1, and then the next value is 0.2, 0.2, I'm kind of picking points at interval 0.1, right? And that's going to give me whatever trend is at that scale. It's like if you're looking at Google Maps at a specific scale, right? If I multiply that value by something smaller, if instead I sample at a smaller scale, right? If I do 0.01, 0.02, right? And I'm just sampling from the picture, right? Like I'm in the real world, I'm placing them in the same place, but I'm actually sampling at different places. It's gonna give me a different look because I'm gonna be looking at more like the smaller detail changes. It's gonna look different, which is why when I changed the value from 2 to 5, it looked like it was bumpier. And so this starts getting a bit more into like more detail, into like more about how Purlin function works. So I might not explain it completely, but basically, if I uncomment this line of code, I'll just change it back to 3. You should be able to see like an overall level of detail and then a smaller level of detail. Yeah. So you see how you got these big bumps, and then you got this smaller bump over here, and that's because I'm adding 2 different values of noise. So I'm not. This is like a lot more complicated. Maybe we can give a workshop at some point about Purlin noise. I'm sure it's like interesting to people, but like this is just an idea of like why is it that it's important to like think about, hey, randomly rotating your things instead of manually doing them, because it leads to shit like this, right? It's not basic, but like get somewhere. Next, so I was talking about linear algebra. Linear algebra is probably the most important math you need if you want to make games. Some people might disagree, but you can't do games without linear algebra. The fun thing about it is that if you don't like linear algebra and think it's like pointless, games will teach you that linear algebra is useful, and it will get you used to it, and you'll be good at it. Like if you want to make games and you're going through it, you're gonna have to get good at it, and like it'll really help. Like making games helped me when I was doing linear because like it helps you visualize some things that you might not like. Okay, things like dot product, cross product, rotation matrices, and stuff like that. It might seem like very theoretical things. So like dot product. How many of you could tell me what the use of a dot product is? Why would you ever need to use a dot product? Anyone? Could you?
I haven't done a lot of platforming physics.
Okay, so this is not to like intimidate you. Only reason I know why a dot product is useful is because I use it so often. I'm not gonna go through the freaking math right now because this is not a linear algebra course.
For like maybe the normal math, I'm gonna get the for lighting. You can use one for lighting.
Yeah.
Which one of those is.
So for example, a dot product. Okay, a quick reminder: you've all seen the dot product at some point, right? It's the dot product is you're thinking the cross product if you're doing this. Yeah. So a dot product is one vector, quote unquote, times another vector, and it gives you a number. How you get that number, you can go check it out again. It's not hard. What that number represents is actually how much of your first vector projects onto your second vector. So if I have a vector like this is gonna suck for the stream, but like for the recording. But if I have a vector pointing in if I'm pointing my arm up and I project my arm down to the ground, so like the vector on the ground to the ground, the floor, whatever. The result is gonna tell me how much of like the vector composing my arm is aligned with the ground. So in what way is this useful? This is useful if you want to know whether I'm looking at you or not. This is useful when you want to, for example, if here's something I was doing very recently. I throw a ball at the ground, right? The ground is like that. Say like you want to bounce up, right? And you wanna like counter all the speed going down, not the speed going forward, just the speed going down, right? So how do you find like the ball is going at an angle? How do you find that in that vector, that angle vector, how much of it is just the down part, right? Because you want to leave the forward part alone, right? You don't want to change that. You just want to get the down part. Well, you project your vector onto the up vector going from the ground, and you'll know just exactly how much of your vector is up. So that's an example. Cross product is going to give you the perpendicular of two vectors. That's very useful because let's see, you've got two things. Like the very basic is like, how do I get that thing pointing out from the ground? It's perpendicular to the ground. So the ground goes this way, the ground goes this way. What's perpendicular? It's up. That's the cross product. So it's very useful for things like that. It's useful for physics. In the assignment that we gave, it would have been useful for you to make the bounce. So am I going 7:30? It would have been useful for you guys to make the bounce. I'm gonna skip the part about where I do the bounce because it's fairly simple. But basically, a lot of people used. Did you guys use the bouncy material, physics material? Maybe. Do you remember? A lot of people used a bouncy physics material and let Unity calculate all this stuff. They put a material that's bouncy and it bounced. And I mean, hey, it made the thing bounce. That's what we asked for. We said sure. All right. One way to do it would be in the game. You can ask Unity, hey, when is my object colliding? Tell it, hey, when has it collided? And when it collides with something that you want to bounce off of, you can ask Unity, hey, what is the normal of collision? Just like I was talking about now, like bouncing a thing, you can ask it, what's the normal of collision? And then you can be like, hey, add a force in that direction. So it'll get you the normal, and then you can just be like, hey, add a force in that direction, and your thing will bounce. And that is very important to understand, to like be able to think about linear algebra like that, because it'll help you do things like that. And also do a lot more complicated things, like what I'm going to get to. I know it's stretching out long. I'm going to try.
How much longer are you going to run for? I have to leave.
You guys have to leave?
Because I have a midterm.
You have midterm tomorrow?
Yeah.
Oh, damn. The only thing I was going to run over afterwards is artificial intelligence. So the last challenge that we asked for was to implement a turret. And this was a bit more complicated. If you guys want to leave, I'm basically going to go through how I would have done it. Like I can post it online. I'm gonna post anyway the recording, if it works. But basically the point is artificial intelligence in games is super important because it gives life to your games. But while it's not as complicated as things like machine learning, the point of artificial intelligence in games is that it has to look believable. It actually does not only has to look believable, but it has to be fun. If you you can very easily make a thing that can. Oh, it's very easy to make a bot that can like.
Not too smart, so then it's no fun. So
Exactly. You want to make it. If you make a tic-tac-toe game, right? Tic-tac-toe, you've all played it, right? Like without knowing any game theory, you get it. You can't lose. If you have an IQ, if you're older than 5, you can't lose, right? You get it, right? Say I want to make a tic-tac-toe game that's fun, and I want the player to win. It's very easy for me to build a bot that never loses, right? It's like every time they put a thing, just like find the exact spot to put. Just find the spot where you have to put a thing, otherwise you lose, right? That's how tic-tac-toe is. Like they put an X, you put a circle where you would lose if you didn't. But I want them to win, so I might make my bot not do that. I might make my bot fail to do that like 25% of the time, right? A lot of stuff in games is like AI in games. The thing about it is that like it does get complex. Like I'm not gonna lie, like AI is like also a very complex thing to do. But a lot about it is making it simple enough for it to run. We can't run a machine learning algorithm on, while your game is running. You can't wait like a week for your frame to render because it's trying to compute what the AI is doing. That would be a boring game. It has to be believable, has to be fun, but it doesn't have to be realistic whatsoever. It just has to look believable. It doesn't have to be realistic at all. It just has to serve the purpose. That's the fun part about AI in games, is that it's serving a purpose that you're defining, right? So, for example, pathfinding, right? Algorithms for pathfinding are complicated. Well, complicated. Like yeah, they're complicated. Your AI doesn't have to take the shortest path. Actually, if your AI takes the shortest path, it's gonna look like a freaking weirdo. Like the shortest path from here to the door is me literally like going on the edge of everything. Not breaking, like there's obstacles, but like being on the edge of everything. No human being ever walks like that. We generally like to keep a bit of distance between us and other objects, right? We might get distracted or whatever. So like you don't like your AI might not take the shortest path. And that's the point. So a lot of AI in games is like that. It's a lot about like how do you want to make it think, and it's a huge field. Like how does the AI make decisions? It's not just pathfinding. There's decision making, whatever. I'm not gonna go over this right now. I'm just gonna go over basically how I would have made the turret in the game. If you guys want to leave, yeah. If you guys have midterms, like feel free to. Man, I had 2 midterms today. I feel you. What exam is it?
It's math.
Math?
Yeah.
Is it linear?
No, it's 16.
262. Oh, it's calculus 4. Calculus 3.
Intermediate.
Intermediate, yeah. Have fun.
Yeah.
Yeah, so if you guys want to leave, feel free. I'm going to continue, and I'm going to basically look at how we would have made this turret. So we wanted to make a turret that would shoot at the player. We can make this in many different ways. I'm going to decide to make a turret that... I'm not done writing this code, by the way. This is going to be slightly experimental, and me finishing this code right now. And so it's going to be fun. We're going to try and make a turret that rotates toward the direction of the player. And when it's facing that player, it's going to fire. And it's going to keep firing at some fire rate. Right? That's AI enough behavior. That's generally how a turret works, right? It tries to turn to track the player, and then it shoots when it gets there. Tons of way to do this. Tons of information you can give it. The thing about AI is that the AI always knows more than the player, and there's no way around that. Like, if the AI wants to know more than the player, it will know more than the player. If the programmer wants the AI to know more than the player, it will know more than the player. Like, it knows as much as the programmer gives it, and since you're making the game, you can make it know everything. So first thing I'm gonna want to do is so let's add a cube, turret. I can disable my random generation because otherwise it's gonna. Gonna make a player. I put the player here. Play. Nothing's gonna happen. I'm not gonna play this to show you because like there's nothing. First thing we're going to want to do is we're going to want to open this code here. I want it to rotate towards the player. So one way I can do this is I'm going to put a game object to say which one's my player. And one way I can do this is to do this dot transform dot look at, which is a function Unity gives us, target dot position, target dot transform dot position. So if I put compiles, what? Oh, whoops. So if I add turret to the turret, and I pass it the player here, and I play. So if I move the player like that, it's literally tracking him. It's tracking him exactly, which is neat, right? That's pretty cool. But we kind of want it like we don't. This is the example of your AI can be very easily too strong, and we want it to be fun. So instead, what I'm going to do is I want it to. So your turret's looking one way, and I want it to want to look towards the player, but I want it to take time to look there, right? That would be more fun. I don't know if we can make this very experimental, and you guys tell me how you want this turret to behave, and we can try and code it. But if you guys are happy enough with this behavior, we can try and do this. This is good. So we're gonna try and make it look towards that direction. So one way we can do this is that we can use a very neat thing called interpolation. So do you guys know what interpolation is? So interpolation is the concept of, you've done high school level math, right? You know when you have a line, right? And you have, well, you know when they give you like 2 points and they're like, find the equation defined by these 2 points, right? And it's like mx plus b is equal to y, right?
Yeah.
A line is defined by infinitely many points, right? Can we agree on this? When you give 2 points and tell me define the line, it's like you're saying, I'm giving you 2 points, define all the other points, right? Interpolation means I'm giving you 2 points, and I want you to tell me what the point between them is. Maybe 50% between, or maybe 30% between, or maybe an arbitrary amount between, right? It's literally kind of like apply a function. So it's like if I give you 2 points and told you find me the function for it, right? And then I said, okay, so what's the function value at 4? You can give it to me, right? If that value happens to be between those 2 points, that's called interpolation. If it happens to be outside of those 2 points, that's extrapolation. Interpolation because it's inside, extra because it's outside. So we're going to use a thing called interpolation, and it's going to be it's linear interpolation because it's like on a line. So basically, if you have 2 points and you tell it like 2 points and tell it 0.5, it's going to return to you the point between them at 0.5. And so using that, we can say, hey, so for example, if I want to go get to where you are, but not like teleport, right? I can say every frame, for example, hey, give me 10%, the point 10% between us, between my current position and your position, right? It's going to give me 10%. I'm going to advance. Next frame, I'm closer to you. I'm going to tell it 10% again. It's going to give me another distance, right? So I'm going to eventually keep advancing, and I'm advancing by a smaller and smaller amount. And initially, I'll be advancing by like much larger amount, but at the end of the day, it kind of gets the job done. There's better ways to make a thing walk towards you instead of like teleport, but you guys get the point, right? You get the idea. So exact same thing. We want to make it rotate. Like, oh, you're pointed this way. I want you to be pointed that way. So instead, how about you point 50% in the middle, 10%, 50%, whatever you want. You kind of decide sort of how you want to do it. The number you give it, the percentage you give it, defines how snappy and how fast it's going to go. Okay? So we're going to get the direction. So linear algebra again. Hopefully you guys are sort of familiar. You guys both comfortable with linear algebra?
Yeah.
So going to get the direction that we want to point towards, which is the player. the player's position minus our position, right? That's going to give us the vector that way, the vector that we want to be pointing towards. That's what we were using before. That's what look at. If I had just done the same thing, it would have worked. I'm going to freeze the y-axis because I don't want it to rotate up. I want it to, like, if my player is here, I want to rotate like this. If he's here, I want to rotate like this. I don't like, if I just unfroze the y-axis, it would do like this, which might be something we want to do. But like in this case, we want to freeze the turret to be like, look, just on the ground. Okay. So we're gonna use a very fun thing. So in Unity, this is way beyond anything. Rotations are defined as quaternions, which is a complicated thing, but basically it just means it's a rotation, and we can tell it, hey, quaternion.look rotation. Give me the rotation it would take to look to this direction. So quaternion is a rotation. If I multiply that quaternion by a vector, it's going to rotate that vector by that rotation. That's all you guys have to understand. That's what a quaternion is. If you guys have done matrices, it's a matrix, which when multiplied by a vector, will transform that vector. The exact definition is way more complicated, but like we'll skip for now. So I'm going to tell it, give me the rotation required to turn to that exact, like how much do I need to turn to you? Give me the rotation, the exact rotation. And if I just did like rotation.this.transform transform.forward, I would transform my forward vector into the forward vector, right? So like I would get my forward vector wherever I'm pointing right now, multiplied by the rotation, and my vector would become this. Instead, what we want is we want to get somewhere in between. So we're going to say the transform.rotation is instead equal to quaternion.slurp, which is fancy way for, what does it stand for again? LURP. The LURP part it comes from linear interpolation. Slurp mean again. Spherical linear interpolation. So it's a fancy way of saying some other mathematical definition of LURPing, of linear interpolation. You'll hear it a lot.
Also another called like LURP, right?
Yeah. LURP is linear interpolation. Slurp is spherical linear interpolation. Slurp is used for rotations because if you think about it, rotation, you're like rotating inside of a sphere, kind of. Can you kind of visualize it? You have a sphere. All rotations can be defined by like any point on the sphere. But that's beyond. So we're gonna just say, point being is we're gonna linear interpolate between current rotation, rotation we want to go to, rot here, and we're gonna give it a speed times time.delta time. Speed is basically how fast we want to go. It's just gonna be a number that we're gonna give it. Times.delta time is how much time has passed since the last frame, so we can kind of make it go smoothly. And here, this this lovely thing here is we're gonna use after. But for now, let's run it. So kind of mostly turning at the same speed. Like it looks like it's pretty much doing the same thing. That's because our speed is super fast. And if I do this, you start seeing how it takes some time to turn. Which, I don't know about you guys, but I think that's a slightly more interesting way to do it. So if I do 0.5, it's going to take some time to rotate towards our player. So we've achieved basically what we want to do. We want to make it turn slowly, right? Without making it think too much. Are you guys following so far? Is there anything super unclear or whatever? I'm just going to set this to 1 because 10 is too fast. So now, next part, we're going to try and go through this not too slowly. Fire when you're pointing at the player, right? So I'm going to put this in another script just to kind of keep it clean. I put this in a script called turret gun, okay? But before we do the turret gun, basically what I want to do is like when I'm pointing towards the player, I want to fire, right? I want to shoot. Let's leave the shooting to be done by the turret gun, but deciding when to shoot to be done by the turret itself. So how can I decide? Remember how I was talking about the dot product, right, earlier? dot product of my current direction and the direction I want to be in. If I dot them together, it'll give me, yeah, if it's equal to the magnitude, or basically if it's equal to a very large number or a specific number, it means that I'm very close. I'm pointing in that direction, right? Because if I'm okay, so dot, like you're gonna see how it makes sense. Dot product of two perpendicular vectors is 0, because there is nothing in this vector that's projected on this. There's like the idea really is like how can I get like the components? I need to like kind of like project it. So this is none of it. This is a small number because it's like the shadow. Like think about it, the shadow, right? As I get closer and closer, the shadow gets bigger. If I just say once the shadow is big enough, hey, once the shadow is big enough, it just means that, hey, I'm like these two vectors are almost aligned. Actually, when it's equal to 1, when the value is equal to 1, it means they're parallel. Because the value it gives you is, you take this vector here, by how much would you need to multiply this vector here to get the projection? That's the scalar dot product. So if I did, one way I could do it is if I did, let's do this here. If vector 3 dot dot, because I'm not going to define my own dot product, it's whatever. This dot transform dot forward and direction, right? If this is bigger than, and like, man, I really hope my math is not super wrong right now, but 0.85 f, so 85% of the way there, I'm pretty sure. We're gonna print fire. Hopefully my math is okay with this. If it's not, you guys can make fun of me. All the things I told you guys about the logic, the theory is correct. I might have gotten the numbers wrong, but so it's gonna say fire. So okay, let's slow down this buddy by bunch. Let's keep it a 1. Let's move. I pause the game right now. Let's move this guy like here. Clear the console. Fire. It's firing too much. Okay, I probably used the wrong value. But the idea is dot product two vectors. Might have done it wrong, but the idea is basically the same. Enough that I'm just going to use the vector dot 3 angle. It's going to give me an exact angle. The reason I use the angle is just because it's an easier way to like think about it. And see if the angle between these two is smaller than 5 degrees, fire. So 5 degrees. And the reason it's the same is because the way to find the angle between angle between two vectors is using a dot product. So as proof that I know my math a bit at least. So we're gonna do this instead. So when it's less than 5, fire, and then let's move this to here. Clear. Hopefully it doesn't fire until it like is sort of in the direction. So if you look here, fire when it's in the direction. So now we've got it firing when it's in the general direction. It's going to keep firing, actually. If I open this right now, it's going to keep firing forever because it's always in the direction. So the player sucks because he's not moving. But it does what we want. Like in general, it's doing what we want. So now let's make the turret gun. This is something I saw that a lot of people didn't get. Some people try to do timing. So one way you can do timing is you keep a counter, right, in your update loop. And like once that counter has hit something, do something. Problem is the update loop runs once per frame. Frame rate is dependent on your computer, how good your computer is. Meaning that if I do int I equals 0, I plus plus, if I bigger than 50, fire. If you have a really good computer at home, you're gonna get shot at more often than me. because your computer runs higher frame rate. Because if I'm running at 30 frames per second, it's not going to hit 50 before at least 2 seconds. You're running at 60 frames per second, you're going to hit 50 the first second. I mean, you're also going to lag, like your game's going to, well, not like, I'm also going to be like running slower, quote unquote, but like you get the point, right? It's generally a bad idea to tie stuff like that.
But is there a way to actually log the FPS?
To check the FPS?
I mean, to log the FPS to certain, like 30 frames per second. 60.
I think you can do it in Unity. You can lock the FPS, but that's one way to do it. You can say, hey, lock the FPS to lock the FPS to 60, and then it's only 1/60 seconds, right? My computer can't run that game at 60 frames per second, so it's gonna run it at 30. So one game that does that is Doom, the original Doom. Runs the game at 1/60. It assumes that you're running it at 1/60 frames per second or 1/45. Remember, at a specific frame rate, and if in its physics for the time, it takes 1/60. So if you run your game at 120 frames per second, the entire game runs faster.
Yeah. I played some PS2 games on PC, and I also got that kind of effect.
Yeah, because oftentimes it's silent. And it's a bad thing to do unless you really have to. Like, the only reason to do it is if it's expensive for you to get the time of your computer. One way to avoid it is you can use a very nice thing. So I used time.time earlier. I'm going to use delta time. Sorry, I used time.time in this one. So time.delta time tells you exactly how much time has passed since your last frame. So if my computer is running slower than yours, time.delta time is going to be bigger than the time.delta time on yours. So if I want someone to move by 5 meters per second, if I do plus equals velocity times dot delta time, right? I'm incrementing it by the exact amount required to achieve that velocity. So that's one neat thing. But also, I don't want to check the time.delta time once per frame. I mean, you can do it. It's totally doable. One way to do it. I'm going to find another way to do it. So here, I'm going to define a fire function. So I'm going to say you can fire every fire rate seconds, and otherwise you can't. So we're going to say when we fire, we can get the current time. Check when was the last time we fired. If more time has passed, if the difference of those two is bigger than fire rate, then we can fire. And we just say that we just fired now. So that way I don't have to check once per frame and be like, hey, bool can fire equals true, because it's like once per frame. It's like easier to do. So here in turret, I can do gun.fire, and if it can actually fire, it's gonna fire. If it can't fire, it's not gonna fire. So if I change this to debug.log fire, hopefully you should see fire spammed on the screen a lot less frequently. Fire, I'm just gonna put plus fire, and I'm gonna put time dot time. There we go, just so we can distinguish them one from each other. Okay, so let's see. Keeping an eye down here. Null reference exception, yeah, that makes sense, because I didn't actually make a turret gun. That's neat. There we go. Now it's gonna work. Turn. Fire 5. Next time it should fire is at 10 seconds. So it's firing once every 5 seconds. We're basically almost there at like getting the behavior we want the turret without writing much complicated code. I saw some people write some weirdly complicated code to try and get the turret. Hopefully this gets the idea that you don't have to write super long code. I think I've written how many lines so far? This is 3 lines of code. I mean, like, yes, I've got a bit more experience, but like, this is 3 lines of code. This is how many lines of code? Like 8 lines of code. We're at like 10 lines of code and we're almost done defining a basic AI, right?
Is there a way to make like the turret have a certain range that once the player actually enters it, it starts shooting at him rather than just like shooting him from across the game?
Yeah. So like I was saying that there's different ways to do things. Yeah, we can definitely do it. So we can do here. So the player, it knows about the player. So we can say only track the player. So this code here, we can only run it if the player is within a certain range. You want to do that?
Yeah. How do you specify? Like, I want to see how you work.
Different ways to do it. You can either okay, I'm gonna show you how I'm gonna do it. I'm gonna show you another way that you could do it. That's like more lines of code, maybe more optimal, but like maybe more optimal for the computer, but like longer to understand. I'm gonna do if vector3.distance. Actually, no, I'm gonna do vector2. Whatever, vector3.distance because
What's the difference between
vector2 is a 2-dimensional vector, so xy. Vector3 is 3 dimensions. So I was initially thinking of like checking just the distance on like the flat distance. So if you're above me or right in front of me, as long like your y doesn't matter basically. But like let's not, whatever. For now we don't have to do that. Like that ends up depending on like how you want your turret to behave, right? But like so vector3.distance, this dot transform dot position, and then target dot transform dot position. If, well, it's not done with that statement. If this is smaller than public float distance detect equals, I don't know, say like 4 units, smaller equal than 4. So now if it's within 4 units, unity units, can I see the grid here? Can't really see the grid. All right, let's simplify this. I'm gonna put the turret at 0, 0, 0. I'm gonna put the player at 0, 0, 0, and then I'm gonna move him in the x direction by 4. So now he's within distance. I'm gonna move him by. Oh, there's the grid. Okay. Okay, so I'm gonna, yeah, so he's now at 5. So if I theory now, if I yeah, not doing much, I move in closer, starts looking towards it. That's one way to do it. I think that's the best way. That's the cleanest way to do it. Another way too complicated way to do it would be to use like the engine detection code to the physics detection code. So you can put I can put another collider that defines like an area. So I can put a collider that's like like a sphere collider here, and I can increase the range like this. And I can say when it enters the collider, say that you can track the player. And if it doesn't enter when it exits the collider, say that you can't track the player. That's a way too complicated way to do it, but it would allow you to define a very specific area. Like if I could use like a specific collider and be like, oh well, when he enters like this edge but not that edge, you know what I mean? But this is the way I would do it. Yeah, we can keep this too. Also, let's have it like not track it if he's too far. It's a good idea. Now fire. Now I'm gonna do the fire. So I want to spawn a thing, right? Spawn a bullet and fire in a direction. A lot of ways to do this. You could write your own code. I'm gonna use a lot of Unity's code. I can get a rigid body which does physics. RB. I'm gonna do game object rigid body instance equals instantiate RB.game object this dot transform dot position. I'm gonna spawn it at the current position. quaternion this dot transform dot rotation. So I'm gonna spawn it at my position with my current rotation. So if it's a bullet, it should spawn facing the, like looking at the player, right? Like it should spawn like kind of rotated towards the player, and then as rigid body. So this is a bit more complicated. I could have done like instantiated the game object, then gotten the component that's a rigid body. I used a shorthand in C# in Unity. I'm gonna say get it as a rigid body, sort of. You don't have to do that, but just to save time. Then do instance dot oh, here, there's one thing I was missing. Fire. When I say fire, I want to fire in a direction. So vector 3 direction. So I'm gonna do instance dot add dot velocity equals direction. So let's see if this compiles. Blah 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 blah. No overload. Yeah, okay. Here I'm gonna give it a direction, right? So the direction is target dot transform dot position minus this dot transform dot position. So that's gonna give us a vector pointing towards the player, right? Actually, no. Let's do something more interesting. Not more interesting. I'm just gonna fire in this dot transform dot forward. Just gonna fire straight in my direction, right? Pretty cool. And then let's say like private public float speed equals 5 or whatever, and then here. So we're just gonna make it as fast as some number that we define. Cool. So that way, like, if the player is further, it doesn't shoot faster. It's always shooting at the same speed. All right, cool. So it's gonna compile. Cannot convert type. Okay, fine. I couldn't do that. I don't remember the exact notation for you to do it, but compile. Now it works. Force. And then let's make a bullet. So let's use capsule. Sure, let's use a capsule, and then let's parent it because I want the capsule to kind of like be rotated, and then let's rotate this around the z-axis by 90 degrees. So this looks like a nice bullet. Hopefully it's rotates properly because I feel like I always have trouble with the rotations. So I'm gonna put here bullet. I'm gonna tell this is the bullet. Oh, whoops! I didn't put a rigid body on it. Put a rigid body on it again. Rigid body. Don't use gravity. Should be good. Add it. Play, and then so if I bring in the player close enough, should be firing. Is it not doing anything?
Maybe you're not in range.
Might not be in range. Let's see.
Yeah.
Oh, there we go. You're right. Oh boy. Oh, okay. So what's happening is that it's the thing is colliding with the bullet is colliding with the cube. So because they're in the same position. So I'm just gonna do a thing. I'm gonna remove your collider. Hopefully that fixes it. And it's also not rotated in the right direction, but I'll fix that later. It's also really big capsule colliders. Let's make this like way smaller. Let's rotate around the y-axis. So let's cool. That should be it. And let's like make it like actually let's make it like way smaller. That might be a bit too small. All right. Hopefully everything works now. Cross your fingers.
It's like it's spitting at you.
Yeah, and it stops when it's not facing you. So what's interesting is I can also make it like, so now that I have all these fields, I can even, turret, I'm gonna make here detection angle, public float equals, let's make it like 15 degrees. So I can make it start firing at you like once it's like within like a range, you know? So it looks kind of like it's not perfect, which is really like often the interesting part. You want to make your AI not perfect, but like kind of good enough, but not too good. Because too good AI is like boring. Yeah, see? So now it's firing towards the player, but it starts firing early.
Oh, so it misses on purpose.
So it misses on purpose. Yeah, we're making it miss on purpose.
Wow.
But if the player stays, he's gonna get fired at as well. So with that, with how many lines of code? 22 to 34, that's like what, 12 lines of code here. Let's count this as 6 lines of code, 20 lines of code. We made a turret. Pretty good, eh?
Should make the bullets chase the camera, like the player.
On the bullets to chase the player.
It's not make it fun for him at all.
Oh boy.
I mean, you don't have to. You could just skip on that.
Type of okay. Public game object target. Oh man, let's cheat this even more. Target equals game dot find with tag player. It's gonna be very hacky. I'm just trying to get the player where he is right now, and do this dot no. So RB dot velocity. Speed equals public float speed equals 5. This dot game object dot this dot RB dot velocity equals target dot game object dot transform dot position minus this dot transform dot position dot magnitude times speed. Should do the trick. Not missing. Cannot convert type. So RB dot velocity times speed. No, not magnitude. That normalized turret. So bullet Let's add a bullet. Target is not set yet. Let's make sure the player is tagged as player. That I wrote this right. And then let's now inject this bullet in. Hope for the best. Hope for the best, people. So it's not rotating, which is not what I wanted to do, but I can fix that with this dot transform dot look at target dot transform dot position. So to make this much more fun. Alright, let's see what this does. Homing missiles. This turret's not firing nearly enough. Like 45-degree angle.
It's just gonna keep firing.
Yeah.
You can make the survival game like this.
I can make what?
Like a survival game. Like how many seconds you can
Yeah.
play with it.
Yeah. Point being, this was not too complicated. Okay, I kind of skipped how I made the bullets go. I don't know if you guys were able to follow. I mean, I just got the direction I had to go into, which is the player minus my position. And I set my velocity to that. And then I also made my thing look at it so it would be rotated properly. Not too complicated. Again, with 4 extra lines of code, I did what you wanted.
Man, your 4 lines of code are like 20 of mine. So.
It just comes with experience. But the point is, so like I called this slide like you can do things 20 ways, 20 billion ways, and the only time you're gonna realize the right way is with experience, is with learning. You're gonna do the wrong way the long way at first for sure. Like there's no stopping it. Like the only way you're gonna learn is by doing it and finding a better way, because the long bad way has a tendency to be annoying to make work. Like elegant solutions, it's called elegant for a reason, because it works, easy to understand, easy to tweak. So long ways, you're gonna realize at some point, man, this is annoying to do, right? And the idea of starting to understand how games work and game engines work is to start being able to think about how can I solve problems with the tools that I have. Sometimes you don't have to reinvent the wheels. Like if I didn't want to do look at, like if I didn't use any of the built-in math functions, like the look at, the velocity, right? If I had to write my own thing that like does the velocity, right? That would have taken me more lines of code, right? But I know what tools I have available to me, and I know that in this case they're gonna serve my purpose well, so I can do it fine, right? If I had different tools if I didn't know about the tool, like when I didn't know about Unity, well, like for example, Zach was like, oh, there's a Purlin noise function in Unity. I'm like, yeah, there's a Purlin noise function. If you didn't know about it, that would take you maybe like a week, well, longer. Like depends on how good you are, but like take you much longer to implement your own Purlin noise. And it's like a huge endeavor. Like Purlin noise is a complicated function to do, right? But I know it exists, so I just cut down like a bunch of development time because I knew what it is. So that's the point, is to kind of start getting familiarized. And the only way to get familiar with it is to make games, to make more stuff, to get it. And like I was saying, like I tell this to everyone when they're beginning, like unless your level of programming is very advanced, like even if your level of programming actually is very advanced, you should get familiar with the tools that you have available to you. And then once you start getting better, and if your programming is better, then you can start delving into doing things you're on your own, right? Like a lot of times we might do our own math on our own because like the tools, they're not enough for what we want to do. Like sometimes you want to do a weird calculation and be like, if it's like rotating, like, oh, like I want to make my thing, like for example, I want to make a ship that like banks, that like does this depending on which side you turn on, right? It takes a few more lines of code. Eventually, you might unfortunately learn why Unity uses quaternions, other than like, so usually we talk about rotations in like 30 degrees on the x-axis, 30 degrees on the y-axis, 30 degrees on the z-axis. There's a reason why Unity and most game engines use things called quaternions, and you might eventually learn it the hard way. There's a reason why NASA used it as well. Otherwise, some satellites might crash and your GPS might not work. So these things you learn just like by trial and error, and like it helps when you have people, but like you might not memorize a lot of the things that I talked about tonight, but you'll just learn it like through experience. Like honestly, like I only learned about these through experience. After coding for a few years, like this year is the first year I've started feeling comfortable enough to be like, okay, I'm having less trouble with doing some stuff or whatever. Like even last year I would have had like a lot more trouble with some stuff. But yeah, so that's all I had to cover. So I'm gonna end it here. I'm gonna stop recording because questions won't be recorded. Thank you guys for coming.